Good afternoon, everybody. Hope you're all doing okay. Hope you had all had a good spring break. Okay, very good. Very good. Okay, wonderful. Let's just wait for one more minute and then we can start the class. Okay, it is 1 o'clock. Let's go ahead and start. Um, Let me first share my screen with you. Okay, you're hopefully seeing my screen. Before I actually start the class, let me just show you what I put on Gradescope. I'm on not Grade. What I put on Blackboard for you. So 001 contents. So you should all have received your graded exam by now. Um, so in exam one, I have the solution. So please look at the solution and understand where you went wrong. Let me know if I have double penalized you. I only penalize you once for a mistake. So if you make a mistake in part A, then I don't penalize you again for part B, C, and D. If it's a different mistake, then I will deduct a few more points. Um, I have an item called exam one feedback for you, and there I've listed some common mistakes that students have made for all three problems in exam one, and there is an alternate solution for problem two, where you have reflections, the reflection of the different inertias. Okay. Okay. Now. If you look at my syllabus, the revised syllabus, the homework four is due next. I mean, this coming Thursday, day after tomorrow, and we have a quiz day after tomorrow as well. So, in order to help you with the homework, what I decided to do for this class was to go through some examples for block diagram reduction, but in particular concentrate on the homework problems. Now, there are a few more examples in the chapter 5 PowerPoint file that we couldn't get to during class, but with what you already know, or what we will cover more today, you should be able to follow those examples. Okay. Please, if there's something that you don't understand how to go from one step to the next, then please reach out either to me, my TA, or even the engineering support for this class. The tutoring services, engineering tutoring services for this class. Then I have more examples in the lecture templates, block lecture 11 and lecture 11B. There are more examples there. So please look at those examples and understand how block reduction is done. I want to quickly recap what we did right before spring break. So blocks in cascade, if you have blocks in cascade, the equivalent transfer function is the product of the blocks that are in cascade. Okay. Now remember, please remember, if I have a signal coming out of this block into some other block, okay, then of course G1 and G2 are not cascaded. So G1 and G2 are only cascaded if there's a clean signal without anything, without any summations, without any, without any pickoff points. There should be absolutely nothing between block one and block two and block three. Then and only then are they in cascade. If they are in cascade, you can take the product of the individual blocks and you get the equivalent block. Please, if there are any questions, please always interrupt me at any time. Please ask me any questions that you have. If you ask me a question, it means you're engaged. Your mind is here. It's very easy for your mind to drift away. So whatever that you don't understand, just blurt it out. You know, you may think it's a stupid question, but there are really no stupid questions. And one question may help someone else or may help 10 other students, or one of your questions may trigger another question in someone else's student, in someone else's mind, another student's mind. So basically, we're all moving together and you're all with me. That's what's important. Blocks in parallel. Remember the two rules for blocks to be in parallel. They must have the same input. This is the same input. They must have the same input, and their output must end up in a summation block. Okay, again, you cannot have something like this coming out and coming into a different transfer function. That is, then in that case, only G2 and G3 are parallel. G1 is not parallel to G2. Hopefully that's clear to everyone. Okay. Okay, so the equivalent transfer function. Thank you. Any feedback from you is also appreciated, because then I know you're with me. You're engaged. Your mind is in this path. Okay. Um, Three blocks in parallel. The equivalent transfer function is just basically the summation of these transfer functions. So you can have you can have you can have a negative here, a positive here, and a negative here. Then it just basically becomes minus G1 plus G2 minus G3. Okay, so the plus minus, whatever you have here shows up here. Okay, feedback form. So you can see that G2, the output of G2 feeds directly into G3. So there's nothing going on between G2 and G3. So obviously this is in series, right? Series or cascade, I should use the correct term. So very important to use the correct term, right? So cascaded blocks. This is also cascaded blocks, right? The output of H1 goes into H2 directly without anything coming out. So this is also cascade. Okay. And there you, and here, this is feedback, right? Everybody sees that, hopefully. Feedback form. So feedback form is basically you have a forward transfer function, feedback transfer function, and the feedback form. So this is the feedback form. Okay. And the equivalent transfer function, is g, the forward transfer function, divided by 1, and then the negative of the feedback. So if this is minus, then you have a plus. If this is plus, you have a minus. So please make sure that you understand that the feedback, whatever the sign of the feedback is, you have the opposite sign here. So 1 plus minus g times h. Okay. So obviously, uh, g here is what? From above, g is the equivalent cascaded transfer function. So what is g going to be? Anyone? Quickly. G2 times G3, right? And H, yeah, exactly right. And H is H1 times H2. Okay. Then you remember the two acronyms that I gave you, SLIM, PROM. So the opposite. So SLIM stands for moving a transfer function to the left of a summation, then multiply all the inputs of that summation by what you moved. Okay, SLIM PROM. So the opposite of SLIM is sum right input divide. The opposite of PROM is pick off right output divide. Pick off right output divide. Okay. So here's an example. I have a summation, and now what I'm going to do is, for whatever reason, I need to move this block g, the transfer function, to the left of the summation. So this is sum left input divide. So that means that the input has to be multiplied by whatever you moved. Is that clear to everyone? So I moved g of s, and therefore I have to multiply g of s by the input, whatever the input is. This one here, I'm moving, use a different color. Green is good. So I'm moving this transfer function to the right of this summation block. So that's sum right SRID, right? Sum right input divide. So any input to the summation block over which I moved my transfer function gets divided by what I moved. So x is the input, x divided by 1 over divided by g goes there. Is that clear to everyone? Is this clear to everyone? Any questions to this? Okay, I'm going to continue. This one here, I have a pickoff point, right? A pickoff point right there. And for whatever reason, I need to move this block G to the left of this pickoff point. So the pickoff left output divide, plod. Pickoff, oh, sorry. This is prom and plod. Pickoff left output divide. Pickoff left output divide. So if I move this block, shouldn't one of those be plod? Yes, is that what you meant, Tony? Prom and Srid and Plod. Okay. Okay, so moving this transfer function to the left of this pickoff, that means the output of the pickoff has to be divided by what I moved, right? So this is the output and this is the output. So I'm so then I have to divide the output, and that's exactly what I'm doing. I'm dividing the output. Oops, sorry, here we go. I'm dividing the output. This output, I'm dividing by what I moved, and the same thing here. Is that clear to everyone? What does P stand for? Oh, P is pickoff point. Just like S stands for summation, P is a pickoff point, and the pickoff point is basically any signal. So this is a pickoff point. This is a pickoff. This is a pickoff point. Okay. So is that clear to you, Veronica? Okay. Okay, good. Good. Please continue to ask any questions. Remember, there are no stupid questions in my class, none at all. I'm happy to answer them all. And like I always say, one question might prompt another question in another student's mind. The more questions, the better. The better, because now I know that more and more students are engaged and are with me. Because this stuff is not completely intuitive. This stuff is something you're hearing for the first time. So I completely understand that you will have questions. It's only natural for you to have questions. So if someone doesn't have any questions at all, it doesn't necessarily mean that they've understood 100%. It just means that they were not completely with me. That's how I'm going to assume. That's what I'm going to assume. Okay, good. So we've gone through the different examples of slim and prom and all of that. Now, what I want to do is I want to concentrate on the homework. So please, with everything that we have said and with the homework problems that we're going to look at together, I'm not going to solve it 100% for you, but I'll start it up so you can finish it. So with all of that, please look at the examples in chapter 5, the PowerPoint file, okay? And look at these two uh, lecture uh, lecture PDFs that are in the template folder. And if you have any questions, you know how to get a hold of one of us. Okay, good. So for the system shown, find the percent overshoot settling time if the system's response is un, under damped. Is it and why? Okay. So basically what we're trying to determine is one equivalent transfer function, right? From here on out, the equivalent transfer function, I'm going to call this as T, which is referred to as the total transfer function. Okay. So the equivalent transfer function T has an input R and the output C. Okay. So what is this? Out of the three forms, you only have three forms, right? Cascade, parallel, and feedback. Anybody? Which of the three forms is it? Exactly. It's the feedback form, right? So you have forward transfer function, feedback transfer function. So G in this example here, in the feedback form, G is the forward transfer function, 25 divided by s plus 15. And the feedback transfer function, H. What is H, the feedback transfer function? Anybody? Anybody at all? Exactly right. Oof. Marissa, how do you get G1 times G2 times G3? We're looking at problem 11. So Zachary, yes, you're right. H is 1. Marissa, I hope you understand. I was looking, okay. Okay, good. Yeah, you're probably looking at a different problem. Okay, so what do we have? T is equal to G, the forward transfer function, divided by 1, the opposite sign of the feedback, 1 plus G, H is 1. So there you have it. And that will give you a second order transfer function. From the second order transfer function, you all know how to compute the percent overshoot, settling time, peak time, and all of that, right? Yes? Okay. Okay. Remember the standard, remember the standard second order transfer function, G second order is B divided by S squared plus 2 zeta omega n S plus omega n squared. You must have a 1 here in order to use this, in order to use the zeta, extract the zeta and the omega n, the S squared must have a unity um, factor to it. Okay, let's look at this block reduction problem. Okay, so the first thing that I do is I look for um, the three forms: cascade, parallel, or feedback. Okay, so if I look at this here, um, do you recognize anything right off the bat? Anybody? Okay, so parallel is correct. So one is parallel, right? So that is parallel, correct? Now someone said feedback. Okay, so exactly. So you see, this is not, this here is not a feedback loop yet. Why? Because this is happening. Because from this, in this loop, in this signal here, you have a pickoff and something is coming out. Therefore, the blue is not a feedback loop yet. So is that clear to all of you? So this is not feedback. So this is not feedback. Okay. Okay, so right now all I have is parallel. Okay, then we're going to see we're going to keep reducing the system till we get the total transfer function between the input and the output. Okay, so let's continue. We have parallel blocks. So parallel blocks. So this is parallel. And so let us take advantage of the parallel blocks. So we have, oops, sorry. We have 4 plus 1 over s, okay? That goes into this summation block here. And then I have a pickoff point. Then I have this 3 over here. And then I have minus, right? That's this one here. Please stop me at any time, okay? I have this. And then I have 5s. I have C. Then I have a feedback going from there to there. And then I have another feedback going from here all the way up to here. Okay, and this is R. So far, so good? Okay, let me continue. Okay, so we're done. We're done, right? There's nothing more that I can do in terms of identifying one of the familiar forms. Everybody agrees with that? Okay, good. So what I have to do is I have to start moving a block right or left of summation blocks or pickoff points. So the first thing I'm going to do is I'm going to move this 5s to the left of that pickoff point A. Okay. So in the exam, if you would please tell me what it is that you're doing. So move 5s left of A. And that's all I'm looking for. Well, that's the first step, that you need to tell me what it is that you're doing. Okay, so if you move to the left of a pickoff, then that's pickoff left output divide, plod. Right? Okay, so if I did that, A is now going to be here, right? Do you see that? Let me not do that. Let me not do that. Let me not do that. Let me not do that yet. Okay, so far so good. So what I'm going to do is I'm going to, let me just copy this over. Let's see if this will work. Okay. Now, when I move the 5s to the left of A, what happens? Yeah, just a second. So this becomes A. Do you agree? Does everybody agree with that? Correct? Okay, good. So Now I have this here. This and this. What do you think happened to those? What do you think that is? Is it a familiar form, cascade, parallel, or feedback? No, not feedback. It's parallel, right? It's parallel because you have the same signal going into the two blocks, right? This is unity block. So you have 3 plus 1, 4. Is that clear to everyone? Okay, um, so what I want to do, apologize. So I'm going to say, maybe make it green. So I'm going to say 3 and unity feedback are parallel. Okay. So let me, oh, yes, you're absolutely right. Thank you very much. Uh, you're absolutely right. Plod, apologize. Yes, very good. Thank you, Tony. So pick off left output divide. So you have to divide this by 3s, by 5s. Correct. Let me use the same color. Okay. Tony, is that clear? Is that correct? Do you agree with that now? So 3 over 5s, 3 over 5s, sorry. So you have to be very careful. So 3 over 5s and 1 are parallel, okay? So if I copy this over, let me add some more space. Okay, so 3 over 5s. What I'm going to do is I'm going to take this out and just add the 1 over here. Is that clear to everyone? Okay, so we've done that, and really there's nothing. Well, there is a feedback form, right? Now the feedback form shows up. Do you agree with that? But what I'm going to do is something else. I'm going to move this 4 plus 1 over s. I'm going to move that to the right of this summation block. This is negative and this is negative, right? The original block diagram had negative, negative, and negative. Okay. Okay. So I'm going to move that to the right of the summation. So sum right input divide thread, sum right input divide, and Let me do that. Oh, need some more space. If I did that, then I would have input, whatever I've moved, I'm moving this one 4 over 1 over S. So let me just move move 4 plus 1 over S to the right of, I'm going to call this B, to the right of B. And this is sum right input divide. The only input, let me add a little bit, make it a little bigger. So the only input to this summation is the unity input, right? So this will go away, and then this will, let me make this a little different here. So this is the same summation block, minus. And now I have moved 4 plus 1 over S to the right of B. This is still B, right? So this is 4 plus 1 over S. So far, so good. But I have to divide. I have to divide by what I moved. So what did I move? 4 plus 1 over S. That's equal to S, 4S plus 1. Do you agree with that? Okay, so this is what I moved. This is what I moved to the right of B. So I have to take every input to that summation and divide. So when I divide, I have the reciprocal of this, which is S over 4S plus 1. Is everybody still with me? Okay. This no longer exists, right? Yeah, this is not 3 5S, 3 over 5S plus 1, 3 over 5S plus 1. So this doesn't exist anymore. Okay, this doesn't exist anymore. Is everybody okay with that? Okay. Now, what do we have? Well, we have this interesting, which is basically one summation feeding into another summation, right? So that means that these two summation blocks can be collapsed. Do you agree with that? Because nothing is happening between this summation block and this summation block. So they can be collapsed. When that happens, let me again copy this over. when that happens, then what do we have? We basically have this is gone. Let this be gone. This is not needed anymore. And this goes over here. Minus. Is that clear to everyone? Yes? Okay. This is cascade, right? And what do we have? Anything else? This is parallel, right? Do you agree with that? So cascade and parallel, right? And what are we left with? We're left with the feedback form. So we have 4 plus 1 over s multiplied by 5s, and we have 3 over 5s plus 1, oops, sorry, plus, what is this? S over how did we get this? Okay, so this one was this 4 plus 1 over s that we moved to the right. So 4 plus 1 over s, and 4 plus 1 over s is 4s plus 1 over s. So that is, what did we, okay. So that's going to be s divided by 4s plus 1. You agree? S divided by 4s plus 1. That's what I have there. S divided by 4s plus 1. Okay, just a second. Veronica, can you explain why s over 4s plus 1? Okay. So the block that we are going to move to the right of the summation is 4 plus 1 over s. Do you agree? 4 plus 1 over s is the same as 4s plus 1 divided by s, right? This is identical. Okay. So 4 plus 1 over s, that's 4 plus 1 over s. And Srid says that whatever enters the summation, I have to divide. I have to divide by what I moved. So 1 divided by this is the reciprocal of this, s over 4s plus 1. Veronica, is that clear to you? Okay. Okay, good. So there it is. And then you can do the feedback form, right? Okay. Let me just add a little more space here. Okay, Tony, what is your question? What if the outputs of the feedbacks were opposite, one plus and one minus? So if that were the case, outputs of the feedback. Okay, so if that were the case, then you would just basically have your, if this were, let's draw this here. So if this were, Tony, you're saying if this is a minus and this were a plus, correct? Okay, then remember I'm saying this is a negative. So you have negative 3, 5 plus 1. And if this is a plus, then this would become negative. Tony, is that clear? Because you have negative s, you have negative s over 4s plus 1 multiplied by minus 1, that gives you positive s over 4s plus 1. Is that clear to you, Tony? Okay, so I'm going to take this out just so that don't confuse the other students. This is negative. This is negative. Okay. Okay. Here again, for the system shown in figure this, find the values of K1 and K2 to yield a peak time of 1 second and a settling time of 2 seconds. Okay. So again, do I notice, I basically want, what I want is the equivalent transfer function, right? T, where you have input is R and output is C of S. Okay. Okay. Well, do I recognize any, do I recognize any of the standard forms? Cascade, parallel, or feedback? Anybody? Parallel. So Veronica, can you tell me what do you think is parallel? Veronica, can you tell me? Okay, 50 and K2. Okay, so Veronica, please understand. This. Are you talking about these two blocks? So these two blocks are not in parallel. Why? Because they don't get the same input and their outputs don't go into a summation block, right? The input to this block is this one here. The input to this block is this one here, not the same input. So Veronica, do you understand why? Yeah, so please be very careful. These two blocks are not parallel, they're feedback form, right? This is the standard feedback form. This is the standard feedback form. So, but I'm going to do this a little differently. What I'm going to do is I'm going to move K1 to the right of this summation A. Okay, so let's see what happens if I did that. Move K1 right of A. So if I did that, then I have K1, I have my summation block, I have 50 divided by S S plus 1. Okay, so far so good. Now let me add some more space. Okay. Now, that's the sum right input divide. That's the SRID rule. So the input to that summation block has to be divided by what I moved. So that makes it K2S, which is that, divided by K1. R of S, and this is C of S. Do you all agree? Wait a minute. I still have, no, hold on. That's not quite right. I have two summation blocks, right? And use a different color. So this is this summation block here. This receives R, and I have minus okay. Do you agree with that? Does everybody agree with that? I basically have moved K1 to the right of A. So this is your A now, right? This is your A. I'm going to call this B. This is B. Okay. So I've moved K1 to the right of A. And when I do that, I have to compensate the input by dividing by what I moved. So I divide by K1. I divide by K1, and I still have the other feedback. Okay. Now, do you see anything that I can simplify? Anything at all, guys? Well, look at this summation block. Parallel, not quite parallel yet. Not quite parallel yet, right? Not the same. Well, it is the same input, but the output is not going into the same summation. But you are kind of right, because this and this can be collapsed, right? Well, I should put it down here. They can be collapsed. So A and B can be collapsed because the output of B is going directly into A. There's nothing happening between A and B. So A and B can be collapsed. And if you did that, then B goes away basically. And the feedback goes into there. R of S. This is minus. This is minus, right? Minus, minus. And now, what do you notice? Now it's in parallel, right? Now it's in parallel. This is in parallel with this. Do you agree? Okay, so that's in parallel. This is in cascade, right? Cascade. So that means I can further simplify this. So if this is in cascade, then I can write 50 times K1. That goes directly in there. And these two, the light blues, are in cascade. I'm sorry, in parallel. So K2S over K1 plus 1. Take this out. And there you have it. So what form is this now? Exactly right. Feedback form. Feedback form where G, the forward transfer function, is 50K1 divided by S plus 1. And the feedback is K1 plus K2S. Any questions? And then the total transfer function, T, is going to be G divided by 1, the negative sign of the feedback, 1 plus G times H. So find the values of K1 and K2 to yield a peak time of 1 second and a settling time of 2 seconds. That's second order form, right? Second order transfer function. Any questions? Okay, so let's look at this. Let's look at this one here. So anything that you recognize right off the bat? Cascade on top. Okay, so this will be cascade, and that, okay, I accept that. So that's cascade, right? Okay. Anything else? Parallel on left, and that is also correct. Same input, output goes to a summation block, so that's parallel, right? There is a feedback form going on here, right? There is a feedback form going on here. This is a feedback form, but we're going to stop with this. We're going to stop with this. So let's see what we can do. So I would say combine combine 10 and 10 to 10 plus 10, 20 parallel. Okay. And step 1, step 2, let me use a different color. Combine 1 over s plus 12 and 20 over s. That's going to be 20 divided by s multiplied by s plus 12. That's cascade. Okay, so far so good. Okay, so let's add some more space here. Okay, so we have the 20. Summation, the same summation, call this summation A if you want. This is A. And we have 20 over s plus 12. Okay. Then we have the feedback of 0.2s. Negative, negative. Yeah, negative, right? And we have unity feedback going to call this B. So this is B, and it basically goes from this pickoff point all the way down to there. That's all we have, right? Okay, so then we have R over here and C of S over there. Okay, so what I can do is, what do you think I can do?
The unity to the bottom 0.25.
Okay, could you say that again, please? Say that again. Whatever you
Can
just.
you add like the unity that's on top to the bottom 0.25 because it's next?
You cannot add it because they do get the same input. they're not parallel yet. They get the same input, but their output goes to a different summation block. The output of 0.2s goes to A, and the output of the unity feedback goes to B. So caller, do you understand why you cannot just add them together? Okay, good. So move, Veronica, you had the right idea. Move 20 to the right of A. So if I did that, let's just work with that. Move 20 right of A. So that's sum right input divides SRID. So I'm going to move 20 to the right of A, just like we did in the previous example. Let me add some more space here. Add a little more space. Let me copy this over. Okay. So that's 0.2s. That's the same thing, right? Nothing has changed. So now I'm going to move 20 to the right. So when that happens, this so you have 20. And then you have that summation block A minus B. Do you all agree with this? I moved 20 to the right of A, so no. Okay, oh, yes, you're right. Why? Because the input has to be divided by 20. Very good. Is that what you meant? I hope. Yes, very good. Very good. So, do you all agree with this now? I moved 20 to the right of A. That makes A come over there, right? And since I'm moving it to the right of a summation block, I have to take all the inputs to that summation block and divide by what I moved. So 0.2s divided by 20. Okay. Now, what do you see? You see that this and this summation block, they can be collapsed. Right? Why? Because nothing is happening between A and B. So collapse A and B. So if I collapse A and B, yeah, just a little more space. So in the exam, please tell me what it is that you're doing so that I can give you partial credit or know what your thought process is and give you more credit. Okay, so what do we have here? What do we have now? If we collapse A and B, so if we collapse A and B, then this is basically A. Oops, go away. $20, and then we have the 20 over S plus 12, S plus 12. And then we have the 0.2 S divided by 20, 0.2 S divided by 20. And we have the unity feedback, right? The unity feedback was coming into A, but it's the same as if A and B are on top of each other, it's the same as saying the unity feedback comes into A. There you have it. and this is your R, and this is your C. Now, do you see any of the familiar forms? Cascade, parallel, feedback. Cascade and parallel. Okay, so let's look at the cascade first. So the cascade is, that's cascade. You agree with that? Correct. And parallel would be, oops, sorry. Hopefully you understand what I'm trying to do here. That's one parallel path, and then the other one is right there. Both are minuses, right? And that's parallel. So you can combine the parallels to make it so H. Let me use it a different thickness. H is the feedback transfer function is going to be what? 0.2s divided by 20 plus 1. Forward transfer function G is what? 20 multiplied by 20 divided by s plus 12. Is it indeed s plus 12? S plus 12, yeah. And then the feedback form, right? Is G divided by 1, the opposite sign of the feedback, 1 plus G times H. Any questions? So we have T. What is the input to T? After all of this, what is the input to T? Anybody, please? What is the input exactly? R of S, correct? And what is the output? Correct? Sam and Tony, thank you. Very good. Output Sam is correct. C of S. There you go. Exactly right. Is that clear to everyone?
Yes, Professor, I have a question, please, about the H, for example, before this one.
Oh, before this example, okay.
Yes, sir.
Oops, sorry.
Oh, I get it. I get it. Sorry.
You got it?
Yes, thank you.
Okay. Okay, and then the last homework problem is this one here. So for the system shown, find zeta and omega n for the output, right? So if you put, so I need for this, in order to answer this, what do I need to do? Find the equivalent transfer function, right? T, where the input is R of S and the output is C of S. How do I find the total transfer function from this? Anybody? Anybody at all? How do I find the total transfer function? It's in feedback form, correct. It's in feedback form.
Professor, is it e to the s is cascade with the inside the block?
Just a second, sorry, my thing is not working here. Okay, could you say that again, please? I apologize.
Yeah, for e to the s, is it cascade with inside the block?
This is you're talking about this one here, right? You're talking about
Yeah.
this problem here?
Yeah, this E, capital E.
Capital E?
Yeah, this one.
Okay. Well, capital E is just a signal. It doesn't, it's not a transfer function. It's just a signal.
All right, thank you.
Okay. So what form is this in? Cascade, parallel, or feedback form? Exactly, Tony. It's in the feedback form, right? Correct. So G, so T is G. Oh, sorry. G divided by 1 plus the feedback, opposite sign of the feedback, 1 plus G times H. H is 1, right? So G over 1 plus G, that is the total transfer function. And once you compute the total transfer function, you'll see it's a second order system. Take the second order system and extract zeta omega n, compute the percent overshoot, peak time, rise time, and settling time. Are there any other questions? Excuse me. Okay, so please look at the example problems that I have at the beginning that I talked about. So look at the example problems, please. And then the book has some more example problems. And then I've gone through some more example problems in the form of the homework over here. So I've just kind of started the homework for you, and hopefully you can complete it, okay? Okay, good. So I'll go ahead and stop the share. Any other questions before we conclude for today? Okay. Okay, well, thank you. Have a good day yourself.